everybody, just some final words on radioactive decay. This is part 2, and I wanted to make sure you understood the percentages of radioactive decay. Okay, so same diagram that I had yesterday. Hopefully you have something like this in your notebook, and instead of drawing the people, you could have drawn dots, and you could have labeled the red dots, for example. You could label them grams of carbon-14 left over, and in purple you can put grams of nitrogen-14, because remember, this guy represents carbon-14, and this guy right here represents nitrogen-14, which is the radioactive product, the disintegration product of carbon-14. So over here, in terms of percentages, we're starting off with this box right here where everybody is red. We're going to say that, in this case, 100% of the atoms that are on this box are carbon-14. And over here, what percentage is there of carbon-14? Well, we said that one half-life went by. So half of my carbon-14s turned into nitrogen-14. So now I have 50% of carbon-14. Then, if I keep going down the chart, down here, half of 50%. What's my percentage? I only have 4 out of 16 of carbon-14 left. That's going to be half of 50%, so that's 25% left. So 25% left. And over here, half of 25%, that's going to be 12.5%. So there's a question in your class of learning that asks, okay, how many half-lives have gone by until we only have 12.5% of our original, our starting radioactive isotope left? So you would do it that way. You would keep dividing your percentages by half. You would start with 100, then go to 50%, then 25%, then 12.5. What's half of 12.5, people? It is, half of 12.5 is 6.25 is what we would have after 1, 2, 3, 4 half-lives, okay? All right, so back to me. I have a couple comments to make on carbon-14. And I'm going to do it with my dog because apparently you guys like dogs. So maybe if you see a dog, you're more likely to pay attention. All right, so radioactive carbon-14 is an isotope. That means that there are other carbons in nature and other elements with the same amount of protons and neutrons. What makes it special is that it is giving off extra, it has an extra neutron. So it's radioactive, it's not stable, and its tendency is to turn into nitrogen-14. Well, carbon-14 has a very short half-life. Its half-life is only 5,700 years. That means every 5,700 years, there's going to be half of that radioactive isotope left. So if, for example, an animal dies today, like a platypus. Platypus died. Everybody has an amount of radioactive carbon-14 in you. It's not bad for you. You just happen to have it in your bones, in your flesh, in your blood. And when you die, you're not going to be getting more carbon-14 from nature. You just die with that same amount. And after 5,700 years of that animal being buried, like that platypus being buried, there's only going to be half of the carbon-14 left because half of it will have decayed into nitrogen-14. So now this platypus is 5,700 years old. The platypus is buried. Let's say 25,000 years have gone by. So that's about 4 half-lives. That's about 4 times that carbon going down its radioactive cycle. So we have only 6.25% left of the carbon in my platypus. So after 25,000 years, we're only going to get a little bit of carbon atoms left. We don't have that many atoms left. So we say that carbon-14 is only good for dating skeletons and bones and living things that are under 70,000 years old. So I'm going to take my board. And Bella, you're going to have to move a little bit, baby. Okay, good girl. I'm going to write that here. So carbon-14, only good for dating living things that were once living. Things that were once living. For dating living organisms. Well, they're dead, but they were once living. That were, let's say, no, I did this the wrong way. 70,000 years and younger, let's say. And the reason for that is that if you get like a dinosaur is 65 million years old. If you get a dinosaur, you're not going to find much carbon-14 at all because it's been 65 million years. All of those carbon-14 atoms, they have most likely decayed into nitrogen-14, so you're not going to get very many. What you can do with dinosaurs, you can get another radioactive element with a longer half-life, and your reference table has several under carbon-14. So that's what I wanted to say about carbon-14. To keep this video on the shorter side, I'm going to move on to volcanoes and absolute dating a little bit. Volcanoes, volcanic ash is also a great way to mark time, because once a volcano goes off, all of that ash quickly goes into the atmosphere and can even cover the entire Earth and blanket the entire Earth in ash, and there's rapid burial, and it buries a lot of things. And it's a really good marker because it happens quickly. I should write this down. Volcanic ash happens quickly and is widespread. And that is why volcanic ash is also a good way to tell time in geology. Volcanic ash equals quickly and widespread. And you can also do radioactive dating with volcanic ash, as long as the volcanic ash has these radioactive elements. Sometimes we talk about uranium. Uranium can be a really good radioactive element to detect radioactive isotopes. There can be an isotope of uranium. And again, all of the half-lives are in the front page of your Earth Science reference table on page 1. Now I'd like to move on to rock symbols, so I'm going to pause the video and bring out my reference table. This is what I mean by page 1 of your reference table. See, carbon-14 turns into nitrogen-14, has a half-life of 5,700 years. Then we have potassium-40. Potassium-40 can turn into either calcium-40 or argon-40, and its half-life, look at that, it's 1.3 times 10 to the 9th power. It's crazy. So that has a way higher half-life. Uranium-238, 4.5 times 10 to the 9th power. By the way, guys, how old is the Earth? It is 4.55 billion years old. That's the same age as the solar system. And this guy, 4.5 times 10 to the 9th power, that's 4.55 billion years old. That is the half-life of uranium. So we still have a lot of uranium isotopes left over from when the Earth was formed and the solar system was formed. And this guy, rubidium, even older, 4.9 times 10 to the 10th power. So this guy hasn't even spent a half-life on Earth yet. All right, but what I wanted to show you today, I'm going to flip through my PDF file until I get over here to rock symbols, because this is the last thing we're going to do in relative dating. Rock symbols, they're really easy. All I want you to know is that when you have the rock names over here in this column under sedimentary rocks, this is page 7 of your reference table, they're associated with a specific symbol. For example, breccia. Love breccia. It's an angular rock, and it looks like this as the rock symbol. Sandstone looks like a lot of sand. It looks like dots. Siltstone has dashes and dots because it's an intermediate, between shale, which is just the dashes, and sandstone. So siltstone is in between. It's got both. Shale is just the dashes. Another common one, limestone. Limestone is represented in bricks. These types of bricks right here. Going down. No, I want to go down, not up. Going down, let's look at the metamorphic rock symbols. Which ones are common? Gneiss is a pretty common one in New York State. It's banded. It looks like that. Hornfels is a pretty common one. Remember, Hornfels is the garbage can of rocks, and it looks like a lot of H's in there. And it can be any sort of rock to begin with that was changed by a contact metamorphism. Oh, I don't know what my computer's doing today. Okay, back to here. So those are some things I want you to be aware of when you're answering the questions. I put a couple questions in the Castle Learning just to be aware that we're going to be talking about rock symbols. That distracted me. That's my Brazilian bird clock, and every hour a different Brazilian bird plays. Okay, so back to me. Okay, everybody, that's all I have for you today. It's a shorter video. I want you to answer more questions on radioactive decay, on rock symbols, and volcanic ash. And that's it for today. There's Castle Learning, 12 questions. If you have questions about it, please drop a comment. Nobody's asked me questions so far, so I'm guessing that you understand everything, okay? And when you go to comment the video on things that you learned, try not to copy everybody else. Come up with your own comment. One section has been really good about this. Yeah, that's all I've got. Okay, private email me if you have questions or concerns. Bye.